Hello and welcome to the second vodcast on wave behavior relating to interference patterns. In this, we're going to look in more detail at the specific equations for this section. S equals lambda big D over little d. What does that mean? The two equations for constructive interference, path difference equals n lambda for constructive, and destructive path difference equals n plus a half lambda, we did look at in the last video, but we can review them again here. Indeed, to review, let's just remind ourselves, if we have double slits, it will produce a characteristic interference pattern consisting of alternating bright maxima and dark or zero amplitude minima. The bright maxima are constructive interference. The dark minima are destructive interference. Constructive interference will occur when the path difference is zero, or one wavelength, or two wavelengths, or three wavelengths, and destructive interference will occur between those maxima. This is, of course, given the assumption, the conditions, that the waves leaving the slits are identical in terms of their speed, in terms of their frequency, and in terms of their wavelength. Path difference, you'll remember, is the distance between one of the slits and a point on the screen, subtracted from the same point distance to the other slit. We can see that shown more clearly in this diagram, where I've taken a somewhat more geometrical approach. Definitions. C, up at the top there, is the first bright maxima. We're just looking at the one on the left here from our perspective, but of course these would also be on the right. They'll be symmetrical about the midpoint. That mid-axis consists of a line M to 0, where M is the midpoint between the two slits and 0 is the midpoint on the screen, which you will remember, given that the distance between A1, the first slit, and A2, the second slit, to 0 is going to be the same, has a path difference of 0, and therefore will be a bright maximum. A1 and A2, as I've described, are the slits, and we've drawn also this point P. This point P lies partially along the line connecting A2, the second slit, and that first bright maxima. We should also define some distances. Little s up at the top is the distance from the midpoint to the first bright fringe, the first bright maxima. Little d is the slit separation, the distance between A1 and A2, and big D is the distance between the slits and the screen. Now, this diagram is a lie, or maybe it's better to say it's an exaggeration, because in reality, for the mathematics of this to work properly, it will require that the distance between the slit and the screen, big D, is significantly greater than the distance between the two slits, little d. That's not really illustrated on this diagram. I've had to compress it in order to show you everything that's going on. But that also means that the mathematics doesn't quite work, because what we should have is that the line between M and C, this dotted line in the middle of the diagram, is going to be at right angles to this line I've drawn here, and there should pretty much also be a right angle between this line at right angles to MC and this line at A2 to C. I've shown that by the sort of right angle symbols here. You can see that on our diagram it's not a right angle, but hopefully you can also see that if we stretch this out, making big D a much greater distance, then it would much more closely approximate to a right angle. This is another way of saying, as you hopefully have learnt in geometry about the law of small angles, that once you get very small angles and very large distances, then often the trigonometric functions can simplify. So tan theta will be approximately equal to theta, sine theta approximately equal to theta. Now, you remember the condition for the first bright fringe is that the path difference is one wavelength. So in other words, A2 to C, A1 to C, those two differences will be different by one wavelength. So A1 to C and P to C will be the same distance. Okay, they will be the same distance. And that kind of distance from P to A2, which is the extra distance travelled along that line, will be one wavelength. Now, if you follow through, we can define a pair of similar triangles. Again, in my diagram, they're not perfectly similar because we've compressed it, but in a real life situation where big D was much, much greater, they would be much, much closer to actually being similar. So the triangle M0C and the triangle A1A2P are going to be at least approximately similar triangles. And that means that the ratio of their two lengths is also going to be similar. So we have the two similar triangles here, and given that the distance between C and O, or the line C and O, which is one of the triangles here, length sides, to the longer side here, M0, will be similar to the distance between P and A2 here and the distance from A1, A2. These are both meant to be right-angled triangles, so we're not talking about the hypotenuse, we're talking about the ratio of the two of the sides. CO divided by MO, or M0, will be the same as A2P divided by A1, A2. Which means that S, because S is the distance between C and O, and big D, which is the distance between M and O, will be similar to one wavelength, which is A2 to P divided by D, which is the slit separation, which gives you the equation here. S equals lambda big D over little d. And there's a question, which is where really we are going with here. I say the derivation of this isn't so important, but the use of the equation is. And so here's just a quick example from a past IB paper, where you have a radio station broadcasting two coherent signals. In other words, they're the same. They have the same phase difference at emission. They have the same wavelength. They have the same almost everything, as we'll see. The separation D is much less than the big distance D from the stations to the receiver R. Point P is at the same difference from A and B. So point P is equivalent to O or 0 in our previous example. And the intensity of a radio signal varies with position. So the radio receiver is moved along the line L, along here, passing through point P. And the intensity goes up and down and up and down and up and down as long as it goes through point P. You should be watching this and you should recognize this situation. Yes, it's talking about radio waves instead of light waves, which is maybe what we were assuming, but they're both EM radiation. This isn't two slits, it's two stations, but it's a similar situation. It's still interference, and you still have a very similar diagram. You're still talking about big D and little d. That's a big clue right there. The question says, deduce that the two sources A and B are 100 degrees out of phase. Well, how do we do it? Well, we know that the intensity at P is 0, because it's marked here 0. Therefore, we know we've got destructive interference. We know that the distance from A to P and B to P is identical. Therefore, the path difference is 0. If the path difference is 0, then whatever the phase difference is here will be the same here. If these two were both in phase, then this would be constructive interference and we'd have a high intensity. But since the intensity is 0, these two must be out of phase. Every time this is emitting a peak of a signal or the maximum displacement, this must be emitting minimum displacement. It must be 180 degrees out of phase. The second part says that the wavelength of a radio signal is 40 meters. Calculate the ratio big D over little d. Again, it's really up to you to say, hey, I recognize that. It's that equation that's in the data booklet. The equation in the data booklet is S equals lambda big D over little d, rearranged to give you big D over little d, which is what you're looking for, equals S over lambda. Then you just got to plug in the information from the equation. The only trick here is to see that the first, well, since we're starting with a minima, the distance to the first minima, rather than maxima, because we started with the minima, is going to be 3, but it's 3 times 10 to the 3, so it's 3,000 meters, and the wavelength is 40 meters, so lambda equals 40. Therefore, big D over little d is 3,000 divided by 40, which equals 75. Since it's a ratio, there are no units. Okay, hopefully that was a helpful look at the derivation, meaning, and use of that particular equation. Thank you very much.